Alright, so I'm first going to cover oxidation and reduction. Sorry, the camera keeps zooming in and out. But so oxidation, this isn't going to be oil rig anymore. Your rules are going to be the addition of CO bonds, so like double bonds, triple bonds. That's going to be a theme. It'll be the addition in general of oxygen. And then finally it's going to be the removal of hydrogen. Peter liked to say that hydrogen is kind of like the nemesis of carbons, or of oxygen rather, so anytime you're adding oxygen you're losing hydrogen. Reduction is exactly the opposite, so it's going to be the loss of CO bonds, double bonds, triple bonds, anything like that. It's going to be the loss of oxygen in general, and it's going to be the addition of hydrogen. So that's pretty much all you need to know for oxidation and reduction. I'll just give a quick example. So let's say, for instance, you have a molecule of CH3, CH2. Let's go C with O and CH3. This molecule here, this is actually a ketone. You should know that because it's the second degree carbon that has a double bonded oxygen off of it. Aldehyde would be a single bonded carbon. Double bonded oxygen off of a primary carbon. So this one's just off of a secondary. So this is going to be reduced into a secondary alcohol. So we're going to rewrite that CH3, CH2. This guy is going to be a CH single bond oxygen. So you see we lost an oxygen over here. So this guy is being reduced. And this one is going to have an H because we're adding a hydrogen. And this guy also needs another H because, well, we added it there, and then CH3 still. So basically this hydrogen and this hydrogen got added and the double bond was removed. So that's a reduction reaction. If we did the opposite, going from this to this, that's an oxidation. If it's off of a second degree carbon, that's a carbon that's attached to two other carbons, it's going to form a ketone. If it's off of a primary carbon, so if we move this OH group here over to this one, and let's just say for the record that this is gone. This guy is now on a primary, and this is going to become, this is actually kind of important, this is going to become a primary, or this is going to become a ketone rather. Wow. An aldehyde, sorry. So CH3, CH2, CH2, and then this guy is going to be a C double bonded with oxygen, and you'll have one H. So this guy here is an aldehyde, and this guy is a ketone. First degree, second degree. Third degree don't do anything, they don't react this way. And then finally the other thing that you need to know is that this reaction is actually going to happen if it's above 140 degrees. If it's below 140 degrees, what's actually going to happen is that this alcohol right here is going to turn into, well, it's going to react with another alcohol like it, so it's going to turn into so on. So you got the oxygen in the center here. Let's move that up there. So you got an oxygen in the center here. This is now ether. That's if it's below 140 degrees. So this guy here, ether. This guy here above 140 degrees is going to give you an aldehyde. This one on the second degree is going to give you a ketone. So that's pretty much the main things you need to know about oxidation and reduction. Now, The other types of reactions that were discussed, because there's 4 different types of reactions. So forgive my writing here, but your 4 different types of reactions are going to be hydration, hydrogenation, hydrohalogenation, and finally halogenation. Now this sounds complex and it sounds really confusing because they're all very close and they all start with, well, the H. But it's easy to remember if you just look at the root. So hydration is just going to be H2O. Or write it as HOH, because that's actually easier to remember, just so that you know that it's going to break apart into an OH group and an H. Hydrogenation just means that you're adding H2. Hydrohalogenation is going to be H plus fluorine, or H plus Cl, or H plus Br, and then HI, right? And then halogenation is just going to be any of these guys, but without the hydrogen, so it's just times 2, so you're going to have F2, Cl2, Br2, or I2. So you can easily group these into hydration and hydrohalogenation are going to be unsymmetrical, and hydrogenation and halogenation are both going to be symmetrical. Now the reason for that, if we form a molecule here, I'm just going to get a random one here, so let's go C, 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 and give this guy a double bond here, so you've got these carbons are forming 3 bonds, so they're going to have a hydrogen and a hydrogen. Now this is assuming, of course, that it's cis. If they're on the opposite ends, they'd be trans. But let's say that this is going to be, let's pick one of the symmetricals, halogenated. So let's say that we're just going to add an F here and an F here, and just get rid of that double bond. This is a symmetrical addition because we've added fluorine and fluorine, they're the same, right? If we did the exact same thing, but this time, let's say we did it with, let's redraw this molecule here. So at this point, let's say you wanted to use one of our unsymmetricals, so let's say H2O, so that's going to break apart into H and OH. So if we threw that on here, Markovnikov's rule would say that the hydrogen would go to whichever one has more hydrogen. In this situation, it's in the middle, so it's going to be random, either or. If it happened to the end over here and this had 2 hydrogens and this one had 1 hydrogen, you pick the one that has 2 hydrogens to get the extra hydrogen. That's Markovnikov's rule, or the rich get richer. But in this case, we're just going to pick a random one. So that gets the H, this gets the OH. That's an unsymmetrical addition. And obviously get rid of that double bond there. So those are the basics of the reactions that you need to know. The one other thing that was discussed is if you're talking about the other guy whose rule we talked about, that's, what the hell is his name? Zaitsev. So Zaitsev's rule is kind of different from Markovnikov's, because Markovnikov is talking about which one of these is going to get the hydrogen. Markovnikov is about addition. Zaitsev is about reduction, about removing I guess it would be oxidation, so adding in a double bond. He basically states that the double bond is going to be more towards the middle of the molecule and not towards the end. So if you're taking stuff away, Zaitsev is going to say focus on the double bonds near the middle. I don't know if I said Markovnikov there, but Zaitsev is about removing oxygen or hydrogen, H2O, and Markovnikov is about adding them, so addition reactions and how it's going to function. In terms of solubility and that jazz, so there's a couple ways to think about it. The main force between alkanes and alkenes is going to be your London forces, because carbon and hydrogen are nonpolar, so it's going to be a nonpolar molecule, which means it's if you're comparing one to another, technically speaking, this one would have a tiny bit higher boiling point just because there's more carbon, which means there's that much more London forces. But in general, what you're going to focus on are a few big rules. An alkane and an alkene, or alkyne, sorry, so C with a triple bond to the C. These guys are going to be more flat than an alkene, so C, double bond, C, double bond, C. So this guy is actually not going to look like this in three-dimensional space. It's going to look more like this. So you're going to have the C with the double bond, and then you're going to have one coming up, one hydrogen, and then you can have cis or trans, right? So it can go up or down, C or H. It can be flipped. It doesn't really matter. But because of this kink, these guys aren't going to lie as flat with each other. So like if you stack multiples up, they're going to have a harder time because of this structure, whereas these guys are going to be totally flat and they stack much easier. So an alkyne is going to stack the closest. An alkane is also going to stack pretty close because they're still relatively straight. But each time you add a substituent, you're basically making it harder for them to stack on top of each other. So two of these molecules would have a lower boiling point than one of these molecules because this molecule is a straight line, whereas this one has that substituent up here, which makes it harder to stack together. Technically speaking, they're very close, but that boiling point does go up ever so slightly because of that. In terms of adding in alcohols, alcohols have way higher boiling points because they have an OH group. So if we've got the C, and then an OH, this guy here is going to have a this guy here is going to have a way higher boiling point because the OH group forms hydrogen bonds. Anytime you have OH groups, hydrogen bonds skyrocket the boiling point because those are going to hold together the molecule a lot more than the London forces from these. Now, conversely, because OH is, if you want to think about it as half of water, alcohols also have way higher water solubility. Which means because this is polar and water is polar, the polar molecule is going to dissolve better in water. It's going to be more soluble. So an alcohol is far more soluble than an alkane, alkene, or alkyne. In terms of other things for solubility, it's kind of just down to, with alkenes and alkynes, it's kind of just down to how many carbons there are and how tightly packed they are, once again. So if you think about like an alkyne, gotta look this up. An alkyne is going to have a slightly lower water solubility than the same amount of carbons in an alkane, just because this alkane will break apart its double bonds or triple bonds easier because there's only one here as opposed to three over here. So that's kind of important to remember. Okay, I'm going to stop that there, and I'm going to make a second one in a minute.